Thank you for having me here today, and nice to see all these people interested in knowledge graph. So you won't see much on results on that particular topic. It's much more directions on what I've seen from the machine learning community and where knowledge graph could help in proper industrial settings. So that's really the main context and the main objective of my talk. So as you've seen so far, machine learning took over in terms of AI, and mainly because of deep learning, and it's mainly about recommendations. It's about tagging people, recognizing objects, detecting objects, and doing semantic segmentation. It's a lot of machine learning and a lot on image processing, and also on text understanding. It's all about business to consumer. It's working pretty nicely, and it's working nicely because they have access to lots and large amount of data that we, as consumer or users, we exposing to the large technology company. If you move to industry, it's a different context. The data that you have might be not as large, and usually you need the experts to interpret information. And this interpretation is coming from experience. It's not necessarily backed up by some data, but by discussions and by further conversation. So here it's a context where you have people in a submarine taking a very critical decisions for the next action or the next operation. And they have access to large amounts, some access to some data, and they have a lot of people with high skills in particular domains, and they need to aggregate all of these informations. And other systems where if you make the wrong decision, it has a huge impact is, for instance, train transportations or automotive cars, or on planes and flights that we're all taking. If we take wrong decisions, it has a huge impact. So it's very important to make sure that when we deploy machine learning solutions in critical systems, that they are trustable, that we have certifications behind, because anything that make a wrong decisions in those systems, contrary to the business to consumer, one wrong decisions may have huge impact financially or life. It's just the nature of the industry that the critical system is dealing about. And this is the market that Thales is in, airspace, space, ground transportation, defense, and security. So all those segments, they are markets. If you deploy a machine learning solutions, then you need to make sure that they back up by some certifications, that you can provide the explanation to an end user. There's not some technology that you can try and test, and if it fails, then you learn from the failure. You'll have a huge impact on press release, for instance. So you just can't make that happen straight away. You need to back up with more testing and more experimentation or more simulation, and that's where experts need to be in the loop. So. And experts means more information from knowledge expertise. And if you want to move towards the next stage of AI, which is trustable AI, this is what you need. So you need valid AI. So when you do something, when you deploy a solution, you make sure that it's valid and it does make the right decisions, and you limit the number of false positives. And responsible AI is another important stream. Preserving AI is another field where you don't really can have access to data from users. They might be encrypted because of a few new regulations that we have seen in California or in Europe in GDPR. That they are more and more concerned about those. So how you build machine learning and systems that deal with privacy preserving. And explainable AI, which is what I will be talking from now on how you build the rationale, and that's where the role of knowledge graph and semantics and much more logic foundation might be used or helpful for doing explanation of AI or machine learning systems. So XAI in AI, so AI, as you know, is not only machine learning and computer vision, it's all the other fields that we all familiar somehow with. So natural language processing, knowledge representation and reasoning, planning, multi-agent systems, search, game theory, robotics, they all field of AI. So if you have attended AI conferences, like broad, wide AI conferences like ISHKAI or IKAI or Triple AI, there are topics that are all about AI. And there are a few boxes that you can see them. But they all have a different interpretation of what's an explanation. So in machine learning, basically an explanation is give me the features that give me the reason why the system makes such a classifications. If it's in the planning, give me the rationale of plugging all those actions together for having this particular objective. So you have some initial conditions, you want to achieve a particular objective, and the explanation is why I did connect those actions. And usually you have some logics behind. And that's the same for reasoning. When you want to do a classification on an ontology, then you apply the axioms and the rules, and the explanation is the axioms that end up validating the particular conclusions. And robotics is the combination of all those explanations coming from the planning, from the search, and the machine learning. It's how you combine all of those explanations. So many different fields of AI, many different levels of explanation, and I'll focus on the machine learning part. So how knowledge graph could help, but before giving you some kind of hints where a knowledge graph could be used for providing explanation in machine learning systems, let me quickly go through what's already out there in terms of explanation. So in machine learning, you already have systems that are defined as interpretable models. So linear regression, logistic regression, decision trees, there are examples of models that have a mathematical shape and that you can interpret the results. You can interpret the final, you have the decision boundary, and that gives you some functions, and you can interpret which variables are more important than another. Naive-based models, they're naturally easy to interpret when you make a decision. Feature importance, dependency plot, and sensitivity analysis, they are the tools that people are using in machine learning for debugging or explaining how they end up with such models. And you have other approaches like counterfactual that explain what you should have been doing to get in the right class, given that you are in the wrong class. So what are the features that you need to change, or the minimal changes that you need to do? So if you move back to the financial example, if you apply to a mortgage and you get rejected, the counterfactual will let you know what you need to change in your condition to get approved. So what are the few variables that you need to change? Is it your salary, your family situation, and so on? They will tell you exactly that. And there are tools for interpretation. Others, much more specific to neural network, which is now the wave of machine learning in deep learning. It's all about attribution for deep neural networks. So it's mainly trying to understand which of the features are the most important in my neural networks, but you back propagate up to the very beginning and try to find out if it's a computer vision, which pixels are responsible for detecting this to be a cat, for instance, to be a dog. And the attribution, and this is what is used. You have also attention mechanisms that just focus on a few parts a few layers, a few parts of the neural nets that focus on particular parts, and they try to identify which part is the most important. So there are other techniques, autoencoders. So you try to learn an abstract representation of individuals. So if you have tons of objects about cats and animals and cars, an explanation in their context is a prototype version of a cat. So it's not a cat, it's like what's an abstract cat. So and this is what you have, well, you can't see much, but here there's the autoencoder part. You have the neural nets in here, and this is the inputs here, and this is the latent space representation in here. And another approach is on the surrogate models. So neural nets might be complex. Maybe you don't want to use attributions, autoencoders, attention mechanism, but you just have the input, the output that your neural network is providing, and you try to simulate that with something much simpler as a decision tree, and you don't really care what's in the box of the neural net. You just say, that's my input and output, just simulate a decision tree for me, and then if I have the decision tree, then I could do interpretation. So this is what basically people in neural nets are doing when they talk about explanations. When I talk to our clients, that's not what they expect in terms of explanations. They expect something that they can use and understand as a human being. But all of those, they provide features and characteristics which might be in the image processing. It might be very difficult to interpret and to make decisions on top. So computer vision, interpretable units, that's some work from MIT when they try to find in a neural net which unit is responsible for identifying a particular piece of object. You have uncertainty maps, saliency maps, where as the community knows in neural networks, from the very beginning to the end, you get much more abstractions of the representation that you have. So there's a lot of, you can see the details, so the projector, I think, issues, but you have GuadCam and you have 15 or 20 techniques that help you identify and see. So if it's, well, I don't know if it's a dish in here, they just try to identify and color which part of the picture is responsible for the particular classification is the classification, and then you have visual explanation. So they all pretty good work. And if you go to NeurIPS, which is one of the main conferences in neural network, or if you go to a CPVR, or to all those major machine vision, machine learning community, it's all about those kind of work. They have very little, if no, work on how you do further interpretations. I detect objects and I can do segmentations. But actually, all those things, they have semantics, right? When we look at the picture in here, we see a car with some sky, and the car is driving on a road, and the road is maybe straight, or is turning right, or is turning left. We do have a common sense that we do reason on, and we know which objects are what. But semantic segmentation, it's about a different paradigm. So my talk is really on what's the role of knowledge graph. Can we use knowledge graph or common sense in explainable machine learning? Is it something we can use? Is it something which is mature? And how we could do it? So I don't have any solution. There's no much work on that. Just here to pitching the idea that it could be a way for helping the machine learning community doing more interpretations. And if you look at all the experts in the field, they all need to move to that extra steps. So that's a picture of semantic segmentation. So you try to segment the picture in different scenes. So here you have human, rocks, and beach, and water, and tree, and sky. It's fine, it's nice. You can get the word associated. You get all those labels because it's been defined by the human. So it's maybe a list of 10,000 or 50,000 labels if you're lucky. And it's part of a taxonomy or dictionary sometimes. But it's not really part of a graph. So what if it's part of a graph and you know that the human is standing on the beach, and if it's playing with a ball, well, most likely it might be volleyball or beach volley, or maybe soccer on a beach. So, and that's the thing you can't really do with pure computer vision or pure machine learning work. So with knowledge graph, then you can go further and start interpreting these results or those terms which are all isolated in a much more common sense way. So what if we use a particular domain graph that could be used for doing this interpretation further? And knowledge graph embeddings is a way to go. If we combine the picture in here and the picture and the graph representation, can we combine the two and get much more sense of what we get for a human? Another example of where it could be applied is here you have a decision tree. I say it's quite easy to interpret, but in this case, as you see, there's many branches and many conditions in those branches, and it's difficult to do interpretation. Can we use graphs somehow to compact those graphs and see that those conditions are kind of the same using a particular graph representation of the domain? And that's what probably the experts might bring and say, I know what my sensors are capturing. I know I'm the expert of the domain, so I can provide further kind of annotations, but in a graph representation, and then do the compact these representations and then interpret that further, because interpreting this one, it's nearly close to impossible. Another thing here, it's a neural network. You can read it from the top to the bottom when you have some data, you have some layers, and you have the output. So it's a classification task here with different layers. There are hidden layers here. You have the graph. And what if we could, well, there's a few work from MIT, as I mentioned, that do network dissections. What if we dissect and identify that some parts are responsible for identifying some shape or some concept, and those concepts are a graph or some kind of set of properties of some objects. And well, if you do this, then you replace some subgraph in the network straight away. And there are a few works already that not applying graph, but applying logics for representing the neural nets with a set of logical actions. And the few works that have been presented recently at AAAI that try to embed those particular parts of the network with some logic statements. What if we consider graphs and much lighter representation for reasoning over those particular layers and those particular objects in here? You can do the same on the output and the output. As I mentioned, you can abstract this with a surrogate model, like a decision tree, and you just forget about this particular part that do most of the job, and then you care about the inputs and the outputs, and you try to see what's the connections in my graph. And maybe my graph is connecting some of the machine learning patterns that have been captured. Another part is the personalizations. So if I see this particular picture as a human, myself, I see it as a train accident, and that's it. And sometimes it's just fine, it gives me right explanations. But from experts from the train authority, they know that it's a train accident between two speed merchant trains of characteristics X33B and Y33C, whatever, what it means, whatever. But at least it might be important from some experts. So if I expose these pictures, I may have different explanations for different persons. So if I explain decisions, if I probably go to each of you, I will explain in different ways. Some people say, I didn't get it. Or sometimes say, well, give me more details. And this is where the graph might help and help shaping much more specific explanation. Well, given time, let's skip this. With it, just recent work we did in transfer learning. You try to use a domain where you have large amounts of data. You build your machine learning models where you have very little data. You try to adapt the first domain. And this work was about how you do the transfer, not by looking at the data, but neither at the distribution, but at the semantic representation. And we get pretty interesting results that looking at the semantic representation of the domain, you can figure out if you can do transfer learning with what kind of result you might get, rather than just testing and trying and failing or succeeding, but at least you know it beforehand by looking at the semantic representation. A more unexplainable AI, I list a list of tutorials and workshops which are already up there. There's one in here which is touching the semantic and the knowledge graph dimension of the explanations. All of the rest is driven by the machine learning community. So there's probably more to do on that space, and the first edition will be in the International Semantic Web Conference. There's a few resources, but none of the resources is about combining pure machine learning with some logics or semantic representations. In terms of initiative, there's a few initiatives here in France and obviously in the US with the DARPA initiative, but there's also one in Canada on explainable AI, particularly on avionics, trying to explain critical systems. So conclusion, so explainable AI is not a new problem. It's a reformulation of past research changes in AI. It has been tackled from the very beginning, from the very inception of AI. It's motivated by real-world applications. And in the industry I am, where we have critical systems, if clients want to have those machine learning systems deployed on productions, they ask for explainability certifications. This is the first thing they ask. And then how you solve this? with the existing machine learning system tools, that's part of the solution, but that's not the full solution. So then how you embed this with semantics, graphs, and much more logics. So yeah, so need more work on joint learning and reasoning systems. And that concludes my talk. And just before that, just the slide I have to put it. So we are opening the explainable AI systems that try to combine the learning and reasoning. So if you know people, if you're interested, feel free to discuss with me. I'll be here today and tomorrow. Thank you.